Okay, so we're coming to the last talk, the conference. The last but not the least speaker is Suyoung Choi from Ajou University, and he's going to talk about Buchstaber numbers and Toric wedge induction.
Thank you very much. And the microphone work? Thank you. Okay, first of all, I would like to thank to the organizers for organizing this wonderful focus program and giving me this nice opportunity to talk my work. And today I'm going to talk about the Buchstaber numbers, which is one of the most important invariant in Toric topology. And also I would like to introduce the notion of Toric wedge induction that is, how to say, actually I made it and I named it. So probably many of you are not familiar with this notation, this one. But actually this is a methodology which is really helpful to prove some properties for Toric manifolds. So I would like to introduce and share with you. Oh, okay. So actually my talk is based on the two papers co-authored with Hyuntae Jang and Matthew Bailey. And the first one has been published from this year, and the second one is unpublished yet, but you can find it on arXiv. Okay, so let me start with the notion of the polyhedral product, but I'm very lucky that because probably all of you are familiar with the notion of polyhedral product because this is the last talk of the focus program polyhedral product, right? So among the polyhedral product, actually, I would like to mention the momentum complex and real momentum complexes. So let K be a simplicial complex. Then momentum complex is the polyhedral product of K with respect to the topological pair D2S1. And real momentum complex is the polyhedral product of K with respect to the pair of topological spaces D1S0. Then you know that there is a canonical circle action on D2S1 by rotation, and there is a canonical G2 action on D1S0 by reflection. So these actions induce the canonical m-dimensional torus action on the momentum complex and the canonical G2 to the M action on real momentum complex. Actually, we are particularly interested in the subtorus which act on the momentum complex freely. So the Buchstaber number is defined, Buchstaber number of K is defined to be the maximal dimension of subtorus freely acting on the momentum complexes. And similarly, the real Buchstaber numbers of K is defined to be the maximal rank of subgroup of G2 to the M freely acting on the real momentum complex. So actually these are really invariant of the simplicial complex. So actually we are interested in how to compute these kind of things and the properties of these invariants indeed. But in general, these two invariants are different, distinguished. So actually in 2011, the Anton computed some specific case of some specific cases for such as the skeleton of simplexes. So, and he pointed out that in some cases, the Buchstaber numbers and real Buchstaber numbers are different. So in general, we know that these two numbers are different. But if we restrict our attention to the class of polytopic cases, then we do not have the example yet. So, and even if you consider a little bit wider class, the piecewise linear spheres case, then still we do not have any counterexamples. So So in this talk, actually, I'm going to focus on the piecewise linear sphere case. So from now on, I always assume that K is a piecewise linear n-1 sphere with n vertices. Then we know that there is some relations between the momentum complex and real momentum complex. So what we know is that the Buchstaber number is less than or equal to the real Buchstaber number, and both cannot be bigger than the n minus n. So in particular, we are interested in the maximal case. I mean, the both Buchstaber number and real Buchstaber numbers are m minus n. Then why we are interested in the piecewise linear case and the maximal Buchstaber number case? Because the many interesting and many important class of toric spaces are covered by these cases. So for instance, the complete non-singular toric varieties and the quasi-toric manifold and topological toric manifold, all such cases, or if you take real cases, then small covers, real toric manifold cases, so all such cases are covered by these cases. But in this workshop, I realized that many people are talking about the toric orbifold as well. But toric orbifold is not covered, unfortunately. But if you are interested in the manifold, then it's okay. So I'm always on the manifold, the world of manifolds, not orbifold. Okay, so this is a very quick and simple examples on such situation. So if K is the boundary of the simple X, then if the simple X is dimension n, then it has n plus 1 vertices. So the m minus n is exactly 1. So then the momentum complex of such simple complex is, from the definition of the polyhedral product, then one can easily check that the momentum complex is nothing but the 2n plus 1 dimensional sphere. And you know that in any odd dimensional spheres, there is a free subcorrection. So in this case, m minus n is 1. And it has the one-dimensional subcorrection. So this is exactly the maximal cases, and the simple complex is the PS sphere. So, and you know that the quotient space the quotient space give the Hopf vibration. So, and the quotient space, orbit space is the CPN. That is the most important example of toric manifold. So this gives us exactly what we need. Okay, so from now on, I'm going to talk about the PL spheres and the PL spheres which admits the maximal Buchstaber numbers. So, but fortunately, the maximality of Buchstaber numbers can be detected by the existence of characteristic map. So here, characteristic map is the map from the set of the vertices to G2 to the n, where n is the 1 plus the dimension of the sphere, K, which is satisfied the non-singular condition. So here is the example. So if you have a pentagon and you define the vectors to each vertices, then you can check the non-singular condition. So for instance, if you take this space, then the corresponding vectors are 2, 1, and 3, 1, and the determinant of this, the submatrix is just -1. So it is a unimodular. So this is an example of characteristic map. Then it is known that if there is a characteristic map over K, then the Buchstaber numbers is maximal. And so for simplicity, I call if K satisfies this condition, the K is said to be toric colorable. Okay. But similarly, the maximality of real Buchstaber numbers also can be detected by the existence of mode 2 characteristic map. So mode 2 characteristic map is is defined similarly. So it is the map from the set of vertices to G2 to the N, but satisfying the non-singularity condition. So this is the example. So in this case, so I mean, if K admits mode 2 characteristic map, then I call K G2 to the N curable. Okay. So, but you can easily see that if you have a characteristic map like this, then take the mode 2 reduction, then you obtain the mode 2 characteristic map. Okay. So that means that the toric curvability implies the mode 2, the G2 to the N curvability. All right. So this is why the Buchstaber number is less than or equal to real Buchstaber numbers as well. So I want to characterize the PS pairs which has the maximal Buchstaber number. So in other words, actually, I want to find all toric colorable PS pairs. All right. So I learned from actually, so in order to do that, actually, I observe one operations. Actually, the wedge, which is called wedge operation. But this wedge operation, actually, I learned from this wedge operation from some combinatorial realist. So probably this operation is known already in combinatorics, but I don't think this is popular operation. So the wedge operation is nothing but this one. So if you have some geometry realization of a simplicial complex like this, then you replace one by the one vertex by the interval appropriately and take convex her, then you get another simplicial complex. That is the wedge operation. But independently on this wedge operation, so the Tony and Martin and the Fred and Sam define the K of J operation independently in 2010. Then, but these two operations are essentially the same. So since the wedge operations is associative and the commutative, so if you take wedge operations successively, then you obtain the K of J operation. So these are the same. So, and amongst the simple complexes, if one cannot be obtained from wedge operations from the others, then I call it seed, or just the seed. Actually, that seed was the main object in the Hyun-Tae's talk just before. So, and let me remark that any simplicial complex can always be represented as K of J, where K is a seed. Then why we are interested in these cases? So because actually this wedge operation or K of J construction operation, it has really nice benefits in toric topological viewpoint. Let me tell you the first one. The first one is actually the wedge operation increases the number of vertices by 1, as well as the dimension by 1. So the differences between the M and N is not changed. So the M mass, let us define the number M mass N by the Picard number of K. Then that Picard number is preserved. And that Picard number is indeed the Picard number of toric variety. So if you have a toric variety, if you have some toric manifold over the corresponding to some fan, and this fan is the underlying simplicial complexity is K, then the Picard number, that is the rank of the Picard group of the toric variety, that Picard number is exactly equal to the M minus N. So this is why we call it M minus N. So it means that our wedge operation does not change the Picard number. And also it does not change the class of the sphere. So if K is PS sphere, then so is K of J. If K is star shape, so is K of J. And if K is polytopic, then so is K of J. So this is also important. And the finally also, this is very important. So if K admits a characteristic map, it means that it's Toric curable, then so does K of J. So maximal Buchstaber, the maximality of Buchstaber number is preserved by the wedge operation or K of J construction. This is very important. And this theorem actually evolved consider this operation, this construction only for toric manifold cases. And after that, the BBCG, Tony et al. So prove the general toric spaces. So let me remark again, the wedge operation preserves the Picard number, polytopicity, and toric curability. So then what we can do, so if in order to consider the characterize all toric curable the PSPs of some given Picard number, then what we have to do is that just to check the seed, it's a seed, right? So if seed is toric curable, then all PSPs obtained from that seed by wedge operation are toric curable. It means they admit maximal Buchstaber numbers. So this is we have some very good tools to attack this problem. So, but if n minus n is one case, then we know that every PSPs is the boundary of simplexes. So in that case, actually they can be, the seed is just nothing but the boundary of interval. There is only one seed. If the n minus n is two cases, we know that every PSPs is boundary of the product of two simplices. In this case also, there is only one seed. But if you consider n minus n is three cases, then there are infinitely many seed indeed. So there are infinitely many seed PSPs. But if we consider the toric curability, then there are only finite and very small numbers of the seed, toric curable seeds. So there are only 31. The boundary of cube, and boundary of pentagon, or the boundary of the cyclic polytope, C47. So 4-dimensional cyclic polytope with seven vertices. So there are only three things. So for each Picard number less than or equal to 3, then there are only a few toric curable seeds, right? So I thought that, okay, so I want to generalize it into the general Picard numbers. So at the beginning, actually, I believe that there are small numbers, many the toric curable seeds, but unfortunately, it was wrong. There are not small. There are so many toric curable seeds. But the good thing is that still, although there are too many, but there is bounded. It is bounded. So I mean, there are finitely many toric curable seeds. So actually, I obtained some inequality for the number of vertices with respect to the Picard number. And if K is a toric curable seed, then M should be less than or equal to the 2 to the Picard number minus 1. That is the inequality what was introduced in Hyuntae's talk. Yes, it's already very long time ago, right? So you don't remember yet. But anyway, so this is the toric curable seed. So from that one, actually, if we fix the Picard number, then there are almost finitely many toric curable seeds. And as Hyuntae mentioned in the previous talk, actually this inequality is tight. So for any cases, I mean, even we consider the M is the maximal case, 2 to the M minus N minus 2 to the P minus 1 case, actually there is one example, and toric curable seed. So now actually I want to I want to consider the Toric curve seed of picard number 4, then in order to compute in order to find all picard number 4, then what we need is that all we need to do is list of all PS pairs for n, which is less than or equal to 11, and we have to check if they are Toric curve. So actually, as far as I know, actually there is no efficient algorithm to find all PS pairs for such a big dimension with n plus 4 the vertices. So this is really hard work to list up this one. So we need some idea, but I don't like to explain the details how to obtain this Toric manifolds. But actually since Matthew has a very good skills for the coding, so we could obtain the whole list of the Toric curve seeds up to picard number 4. So as you see, so for picard number 1, 2, 3, then there are only 5 the Toric curve seeds. But for picard number 4, actually there are 3,000 many Toric curve seeds. So it's too many. But anyway, the important thing is that actually we have the list. So it means that the PS pairs of picard number 4, which is Toric curve, can be obtained from one of them by a sequence of wedge operations or K-obj construction. So that means that the characterization of PS pairs of picard number 4 is done. That's point. So, question?
That indicates that Matthew was 3 years old. 1998.
Yes. Yes. He's okay. Okay, so anyway, the complete list and codes can be found in the Matthew's GitHub repository, and you can find it. Okay, so now actually we have a complete list of the Toric curve picard numbers of the picard number 4. Then the next one, what I wanted to is that actually I want to use it to solve some great problems in Toric topology. So actually, what I need is that actually the wedge operation is useful not only for considering the existence of characteristic map, but also the classification of characteristic maps. So I mean, as actually this is also mentioned by Hunter in his talk actually, but let me say again that if actually, for instance, if you have some k, for instance, this is the square, and take a wedge operation at 1, then you obtain this one, right? So replace this vertex by interval 1, 1, 1, 2, then you obtain this one. Then let's consider some characteristic map over these operations. Then you see that if you consider the link of these new vertices, then if you consider link of this one, then you obtain the square. And if you consider the link of this vertex, then you obtain another square as well. But those squares are isomorphic to k, original k. So it means that if you have a characteristic map of the wedge of k, then you also have the 2 characteristic maps over k, right? So this is the general theory. But what I did with the Hanchar in 2016 was that we can do it conversely. So if you have 2 characteristic map over k, then they can obtain, then there is at most one simplicial complex, the characteristic map over wedge of k whose projections are the given two guises. So it means that if you have the all information of the characteristic map over given K, then you can construct all characteristic map over the wedge of K. Okay, so then classification of toric spaces, the problem of classification of toric spaces is nothing but the classification problem on just on just seed PS pairs. So the problem become very small, right? So actually the reasonable became the reasonable problem. So using this idea, actually I would like to suggest one methodology which can be applicable for general problems. So which is called toric wedge induction. So now you have some theorem for toric manifold. Then what you have in order to prove or disprove whether this theorem is correct or not, then what you have to do is that you first check whether this property holds for all toric spaces over seed first. And next, you can check whether if these properties hold for two characteristic map over L, then you should check whether the wedge of this characteristic map and over wedge of L holds or not. Do you understand what I mean? So actually, to prove some property, then what you have to do is that actually as a basis step, you just check whether this property holds for all seed first, and then this property is you should see that this property is preserved by the wedge operation or not. Right? If it is preserved, then it means that this property holds for arbitrary the toric manifold of given Picard number, right? So I used this idea to prove some properties. So actually for showing the projectivity. So in 2016, actually I have shown that the Picard number 3 toric manifolds are projective. Actually, this theorem was originally proved by Kram-Schmitz and Stompers in 1991, but our method is totally different and much easier than their idea. So what we did was just because any Picard number 3 toric manifolds are obtained from the pentagon. So I just check the projectivity of the toric manifolds of pentagon first, and this if you obtain the two projective ones from the projective one from wedge operation, then I prove that this is the projective as well. So using that method, actually I could the projectivity, and also I could prove some more projectivity in different class, and also I could answer some question given by Chen Fu Huang in 2014, corresponding to the geometry of the toric manifolds. So actually, yes.
What's the test for projectivity which you use? How do you detect projectivity?
Actually, I use the Shepard diagram. So actually, by taking a Shepard diagram of the characteristic map and just to see how if we take wedge operation, then how the points goes, then actually I prove that number should be some interior of the region, then so we could solve it. Actually, because Shepard diagram in that case is just 2-dimensional, so we could do that. And so actually, this is the Wikipedia of toric variety. So if you Google it, the toric variety from toric variety, then they say the toric variety, often provide a testing ground for theorem in algebraic geometry. But as far as I know, actually, although this is true statement, but this is really how to use, how to check whether some given property holds for Toric varieties or not. So as far as I know, many cases are for low dimensional or low Picard numbers, Picard number 1 or 2, something like that. So since the reason why we cannot use this one as a testing ground, because there is no complete explicit classification, right? So since we have the explicit classification and we have very good methodology, the Toric wedge induction. So I think now I can say Toric variety can provide a testing ground for theorem. So if you have any problems, then I can solve it. So please let me know. Only for Picard number 4. Okay. So then let me show you one interesting application. So actually it's called the Lipton problem. Actually this problem was discussed yesterday. So I'm very happy to tell you the result on this one. So actually at the beginning, actually I told you that there is no known PS pairs whose Buchstaber number and real Buchstaber numbers are different, right? But actually in the class of polytopic cases, actually there is even stronger question, which is given by Professor Ji Liu in 2011. So that is now called the Lipton problem, that asks whether for any K which is polytopic simplicial complex, then is every small cover M over K the fixed points of conjugation on some quasi-Toric manifold? This is the question. So in terms of characteristic map, that is this one. So, but the polytopicity in this problem, actually, I don't think the polytopicity is essential. So we can replace the condition of polytopicity by the PL sphere, piecewise linear sphere. Then if let K be a PL sphere, then the Lipton problem is equivalent to that for any mode 2 characteristic map over K, is there a characteristic map over K such that this following diagram commute? So this is the Lipton question, right? And furthermore, we can also ask an even stronger question on this problem. So that is actually as I told you, the existence characteristic map is corresponding to the maximal the torus subgroup freely acting on the momentum complexes, right? So then, and this is the pretty circle, the dimension of the torus subgroup freely acting on the momentum complex of and this torus subgroup, the dimension is n-nks, right? So then actually we don't need to assume that this kind of maximality. So we can ask the stronger version. So given a subgroup of G2 to the M acting freely on real momentum complex, then we can ask whether this action induced by a subtorus of Tm freely acting on Gk. This is the general question for Lipton problem. But the Lipton problem case, actually, we know that any 3x3 0-1 matrix has the determinant either 0 or plus minus 1. So actually, the Lipton problem is automatically true for the dimension, for the dimension n less than or equal to 3. All right. And we can use a similar argument for dual characteristic map. Then also the Lipton property holds for the case when also when m minus n is less than 3, less than or equal to 3. So it means that the Lipton property holds for the case both the small dimension case and small Picard number case, right? So the very beginning step for Lipton property is to solve these cases. For n is 4 case or n minus n is 4 case, right? But unfortunately, I have no idea about n is 4, so I drop out the cases. So I want to tell you about the lifting problem for n minus the Picard number 4 cases. But in this case, actually, we need a little bit modified version of Toric wedge induction. So just very simply speaking, actually, we make the basis step bigger and we reduce the inductive step smaller. So we just remain the inductive step is just a canonical extension. So or the M of J construction, what in the term of the K of J construction. Then if we put on this canonical step parts as an inductive step, then basis step is bigger, but still this kind of Toric wedge induction holds. We could prove that. So this is the one good, but this base step can be detected by the injectivity of the dual characters map. So this makes sense. So let's solve the lifting problem for n minus n is 4. The inductive step is quite easy because this part, I mean the inductive step deals with only the canonical extension. So every argument are very easy. So this is quite easily. This is done quite easily. But the problem is that the basis step. But now let us consider the binary metroid represented by all non-zero vectors of G2 to the 4. Then there must be 15 vectors. Then the binary metroid has 840 facets. Then among them, we can easily check that 835 facets which are the determinants plus minus 1, but only 5 facets has the determinant plus minus 3. Okay, so by using the dual characteristic map, and I didn't explain what K bar is, but this K bar is the dual complex of K from the viewpoint of Gale diagram, Gale duality. Then if there is an embedding K bar to this metroid, then we guarantee the G2 to the n correlability. And so if the image of lambda alpha is not one of the 5 facets for any facet sigma, I mean these five facets, then it means that if you take this image, although this is G2 to the 4 vectors, but we can regard them as a 0, 1 vectors, right? 0, 1 vectors, but still determinant is plus minus 1. So in these cases, we can say that the lambda alpha has a lift, right? So as a base step, actually, we could show that if K has facets fewer than 168, then we can take some appropriate representation of K that's image does not contain any of the 5 facets. So we have very strong lemma that one. So if K has a facet fewer than 168, then any of lambda R has a lift. Okay, so that in the base step, actually, we have to see then, okay, then which one has more than 167 facets, and the dual character map is injective. We have to check it, but fortunately, we have the list, right? So we can check every cases, then we can find that there are only 6 pairs, and for those cases, actually, we can construct the characteristic map directly, the characteristic map for each mode 2 characteristic map one by one. So we have this result. So every mode 2 character map over PL sphere with the n minus n is 4 has a lift. And furthermore, I didn't explain detail, but with some other small ideas, then we could show that this one. So you could let K be a PL n minus 1 sphere with the m vertices satisfying n minus n is less than or equal to 4. Then every subgroup of G2 to the m freely acting on IGK should be induced from a subtorus freely acting on the momentum complex. Okay, this is done. Thank you very much.